All right, the next application of integration that we're going to look at is finding the volume of rotated solids. Okay, I'll get to that in a little bit, but first I want to remind you of what we first did when we first learned about integrals and what they were. What we were doing is we were trying to find the area under a curve, and so we would make these representative rectangles. Okay, let me make a good one here. So we'd say, okay, if we have a rectangle like this, and we can find the area of that rectangle, we're just going to make a bunch of these rectangles and add them all together. And that became the integral. Okay, we said, all right, the height of this rectangle would be the difference between the function, okay, because everything on this line is the function. So we said, okay, it's the function minus the bottom, which would be 0. Actually, in this case, since we're kind of flipped over, we'd say, okay, top is 0, and then we're subtracting our function value. Okay, and then that would be our height of this rectangle, and our width was the thing that was getting smaller and smaller, smaller. Okay, so it was our change in x, our delta x. Okay, and then we were adding all these rectangles up as our x went to infinity. Okay, and this became our integral. So when we were finding our area, we said, okay, well, we're just going to call it the integral. We're going to integrate from a to b, and we're going to take the height, which is basically just the function. Okay, in this case, it'd be negative because it's below, times the width of our rectangles, which is dx. Okay, and we're going to kind of build off of this concept for finding volume of rotated solids. So first, let's figure out what rotated solids means. Okay, we're going to deal with this same representative rectangle, but now we're going to take this rectangle and we're going to rotate it around our x-axis. Okay, so I've got a better picture. I've got the same function loaded up here. Okay, so I've got this same picture, and what I'm going to do is I'm going to have a rectangle. Okay, so my rectangle would be this thing. Okay, it's this wide, and it's coming down here, but now I'm rotating it around. Okay, so when I rotate this rectangle around, I get this disc. Okay, so, and if I were to rotate all of them around, I'd have this solid shape here. Okay? Okay, so here's another kind of look at what the rotated solid would look like. So I've got the same function here. And this is your x-axis. This is your y-axis here. Okay, actually this is where the y-axis should be. But as I rotate it around, so this is where my curve was, and now I'm taking that represented rectangle, okay, and I'm spinning it around, but I'm doing it for every rectangle that would fill up this area. So I get this rotated solid. Okay, so it spins around and makes this solid green shape that you can kind of see some depth here if I spin this around. And so I've got this solid mass now that I got from rotating the area under a curve. Okay, and I want to know the volume of this shape. Okay, so we'll go back here. So in order to do that, I'm going to take all these discs that I get, kind of like when we had the bunch of little rectangles that we would add up. I'm going to find the area of each disc. So let's look at what the area of each of these discs would be, and then figure out how we're going to add them all up. Okay? So if I've got one disc, let's see, kind of get one that fits on here. Okay, so this would be my disc. Right from the side view, it would just look like a circle from the front. Okay, oh, that's pretty close. So this is the front, okay? So this is from the side, but if I look head on, this is the disk that makes up this shape here, okay? Now, the area of this disk is the same as the area of any circle, okay? I'm going to have some radius, r, and the area would be pi r squared, okay? That would be the area of this disk. Now, as I move and change the representative disk to the left or right, the thing that's going to change is my r, and it's going to change with respect to where it is on the x-axis. Okay, so what I would be doing is I'd be adding up a bunch of these disks. So my width of my disk here, this is going to be like r dx. So really what I'm doing is I'm integrating. So the thing that's getting added up is my area. I'm adding up a bunch of areas, just like, yeah, I'm adding up a bunch of, so I've got the area of the disk times the width of the disk. Okay, this is area of the disk, width of the disk. So I'm going to have a bunch of these added up and taking the limit as the width gets smaller and smaller and smaller. Okay, so basically I'm adding up the volumes of these thin disks as they get thinner and thinner and thinner. Okay, so let me show you a different representation of this step too. Okay, so this is kind of what I'm talking about. If I were to make a bunch of wide disks and add them all up, that would be a good representation or a good approximation of what the area or what the volume of this solid would be. And as these rectangles got smaller and smaller and smaller and more and more and more of them, I'm going to get closer and closer and closer to the actual volume. Okay, but each one of these disks is going to have its own volume, and it's going to be, okay, the area of the circle times the width of the circle. So that's basically what the integral is. Okay, so this is our formula to find this. Now, the r is the height, which is really just our function value. Okay, so r would be our function value. It's nice that it's squared because then we don't have to worry about the minus sign because we're squaring it, so it's always going to be positive. So in this case, our r is going to be our function. Okay, so what we'd have here, since this is my function, I'd be doing the integral from a is 0, b is 3, from 0 to 3 of pi r squared. So r is this. This is the radius of my disk. Okay? In that case, this gives me the value of r at any x value. So I'd have x cubed minus 3x squared squared. This squared comes from squaring my radius times dx, dx being the width of our disk, or the width of the disk. And this is what I would integrate. Okay, and this one I would just square out. So I can pull this pi out front. 0 to 3. I have x to the 6th minus, let's see, 6x to the 5 plus 9x to the 4 dx, and then integrate each one of these. So it'll be 1/7 x to the 7 minus x to the 6 plus 9/5 x to the 5 evaluated from 0 to 3. Oh, and I've got this whole thing times pi. Okay, so that would give me the actual area, or actual volume, sorry, volume of the rotated solid. Okay, so the basic formula for the disk method, okay, which works whenever there's no gap. So if you're rotating around a certain axis, and your axis is completely touching every part of your function, or the rectangles that are being rotated, you can use the disk method, and your volume is pi times the integral of your radius, which is a function of x, squared dx from a to b, okay, depending on what a and b are. Now, you can also rotate with respect to the y-axis, okay? So if we were to just turn this around here, okay, so if we had a function in terms of y, which is completely possible, if we had a function of y, okay, the only thing that changes is that our variable would be y and not x. Everything else would be basically identical. We'd be rotating this way around the y-axis, and you'd be taking the integral with respect to y instead of x. So it would look the same. So this is if you're going around the x-axis. And if you're going around the y-axis, it would look the same. It would just be the volume. So I guess I shouldn't have a variable in here. I guess, well, yeah, this one's a volume function in terms of x. This would be a volume function in terms of y. It would be the pi times the integral from, we'll say, c to d, because c and d will now be y values. Okay, this would be from c to d of r as a function of y squared dy. So it's just a change of variables, and it's just if you're rotating horizontally instead of vertically. Okay, let's look at another one. Okay, because you're not always going to have these nice, perfect circular discs. Sometimes you're going to have rectangles. So if we put our little rectangle in here, okay, you're going to have a rectangle that doesn't come into contact with the axis you're rotating around. Okay, so if I take this rectangle and rotate it around, I can show you what this looks like. Okay, so this is the same picture that I had. Here's my representative rectangle. If I start spinning it around, okay, I'm going to get a washer. Okay, so I get a nice washer. And I'm going to have a bunch of these washers that I'm going to add up together. So, let's see. So, and the washer is going to change. Okay, so as I move to different parts, the washer will change shapes and things like that. So it'll have a different area. But we can write an equation that relates the area or the volume of each washer with respect to our x-axis. Okay. And if we add all these washers up, okay, we would get the volume of this rotated solid. Okay, so we get this solid rotated figure, and that's what we're actually finding when we add up all of our rotated washers. Okay, I can kind of give you a cross section here too. Okay, so I've got my washer that's rotating around. Okay, so this is kind of a cross section of my solid figure. I would have this as a solid figure that goes all the way around. I hope you guys kind of get what I'm trying to show you here. Okay, and this, I'm going to have different washers that represent different parts of the rotated solid. Okay, so let's take a look at this one. So now, the height of my washer, if I want to find the area of a washer, or volume of a washer actually, okay, so I'd have the washer, and it's got some thickness to it. Okay. So it'll be like this. So I've got this thickness here. This thickness is this. This is my dx really. Okay. And so volume is area times thickness. So the area of this washer would be the area of this complete disk, okay, with a radius of r, which would be like the top. Okay, so this is my square root of x function. So we're going to call that big R. Okay, that's our big radius. So let's make a different color here. Okay, this is big R. And then I'd subtract the area of the hole, which we'll call little r. Okay, so I'd take the area of this. So let's see. So this would be a big R. And I would need to subtract this part that's not part of it, little r. And that would give me the height of my representative rectangle, which is really this. Okay, that'd give me the height of that. And that's really what I'm rotating around. So if I can find the area of that times the thickness, that will give me the thing that I need to integrate. Okay, so in this case, what we're going to have is the area of the big circle, okay, which is pi times this thing squared, okay, so square root of x squared, minus the area of the little hole, which would be this thing squared, oh, so it'd be pi, yep, so right now this is the area of the whole thing. I need to subtract the area, so pi r squared with a little r being the inside function squared. Okay, and I need to integrate this with respect to x. Okay, because that's just going to allow me to move and add up all the washes that I would get from that. Okay, and we can simplify this a little bit. So this, remember, is big R. This is little r. So in the general formula, I could pull a pi out. So I'd have, this is the washer method. Okay, the volume would be pi, since that's a constant, times the integral of r, which is a function of x, squared, minus little r, which is a function of x, squared, dx. So let's go through this one. So I'm going to have square root of x squared minus x squared squared, pi in front, dx. And I'm going from 0 to 1 because I want to stop at 1. Okay, so I'm integrating. Okay, this just turns into x minus, this turns into x to the 4th. Okay, so then I get this still as a pi. So when I integrate, I get 1/2 x squared minus 1/5 x to the 5th, evaluated from 0 to 1. Then whatever this turns out to be, I'm going to multiply by that pi on the outside. Okay. So when I put 1 in, I get 1/2 minus 1/5, which would be 5/10 minus 2/10, which is 3/10. Okay, minus the thing I get when I plug in 0, which is 0, so it's 3/10 times pi, so it's 3 pi over 10. That would be the volume of our solid that we have. Okay, if I had this whole solid, the volume of this solid is 3 pi over 10. Okay, units cubed, which is what they have here. 3 pi over 10 units cubed, whatever your units are. So if your X and Y axis are labeled in feet, it'd be 3 pi over 10 cubic feet of volume. Okay, so make sure you've got the washer method formula down and that you kind of know, the big R is the top function, the little r is the bottom one. And for the disk method, make sure you've got this formula. Big R is the function. Okay, and the washer method could be done with respect to the other direction also. We just change all these to Y's. Okay, so those are the first two methods, and then there's one other method for finding rotated solids that I'll put in the next video. These are the two that you use for the first worksheet, and then the other one will be for the second worksheet.